microphone? Perfect. Hi, can you hear me? Can you hear me when I nod my head like that? Okay, good. Hi. Hi. I'm Assaf. I'm going to talk with you today about efficient assignment and the Israeli medical match. So when I say assignment, I mean we want to assign objects to agents, and agents have preferences over objects, but objects do not have preferences over being assigned to a certain agent. When I say efficient, I mean I want to make everybody happy in some sense. I'll make this sense more explicit shortly. And I'm going to use a case study of the Israeli medical match that we recently redesigned. 2 months ago, we ran our program, and I'm going to tell you a bit about this market, and then I'm going to mention a few mechanisms. Some of them you probably already know. For example, random serial dictatorship was probably mentioned already, but I'm going to repeat that. I'm going to talk about the probabilistic serial that I don't think was mentioned in this summer school. The competitive equilibrium approach that Eric described for the combinatorial assignment problem can be applied somewhat differently for this problem that I'm going to mention, that I'm going to describe. And then I'm going to talk about the mechanism that we actually chose to solve the medical match. Because all three mechanisms that you see here use a very fundamental mathematical theorem called the Birkhoff-von Neumann decomposition theorem. I'm going to also prove that theorem to you because I think it's a great tool to have. And finally, I'm going to talk about a certain thing that kind of made our job a bit more difficult, which is couples in the medical match. We have couples in the medical match, same as we have in the American medical match. But here, because it's a one-sided assignment, we need to treat it a bit differently than what we do in the two-sided assignments that Al mentioned a few days ago. Maybe if I'll have time, I'll also mention the Israeli psychology redesign that was finished 3 days ago and is also very interesting. So, medical studies in Israel. Becoming a doctor is very long and very tedious track. You have to do 6 years of studies. Then you have to do about 6 months of exams. You're not taking the exam for 6 months. You're studying for 6 months and then taking an exam. You have 1 year of internship. And then you have between 3 to 6 years of residency, depending on your specialization. If you're doing something very difficult, you might do even slightly more than 6 years. So it's a very, very long track. And despite the fact that it's long and very demanding, it's still in high demand. People really want to become a doctor. So we have every year about 1,500 people applying for medical schools in Israel. Out of them, about 500 get admitted. Out of those who did not get admitted, we have about 500 going abroad to study medical studies abroad and then come back to do their internship in Israel and their residency. But we're going to not talk about those who are studying abroad because this is a different match, okay? One more reason that we have a lot of doctors in Israel is because almost everybody's mom is Jewish, and Jewish moms like their sons and daughters to be doctors. So we have or lawyers, but we have a lot of doctors. And by the way, those that are not Jewish are minorities, and minorities also like to study medicine. I also wanted to mention, okay, so we're going to talk about the 1 year of internship, okay? Right after you finished medical school, you took your exams, now you need to do an internship. You can do it in one of 23 hospitals across the country, and you need to match to an internship. When you do your internship, what you do is, it kind of depends on the hospital. It could be slightly more boring or slightly less boring, but it's going to be boring. It's going to be mostly paperwork, doing night shifts in which you cannot actually treat patients. You cannot prescribe medicine. You cannot prescribe drugs, for example, because you are not a doctor yet. You are only going to be a doctor after you finish your internship, and you're going to be paid very little. Okay. Why do we have internships? So first of all, Israel pays for the medical studies. It subsidizes the medical studies. So we want the doctors to give back something to the state. It looks good from a political point of view. It also helps us a bit in preventing people from doing their medical studies in Israel and then going to work in the US, because you have 1 year where they actually have to work in Israeli hospitals. So it reduces the probability that they will run away right after medical studies. And obviously it helps the hospital because it gives them qualified yet very cheap labor to use for, paperwork and other stuff. Kind of things that are not exactly medicine, but not exactly something that you could hire anyone to do. And because the state actually controls the allocation of students, you can bypass the rural hospital theorem, and you can just allocate doctors to rural hospitals as you wish. Yes?
So doctors are, residents are assigned not by their preferences?
Well, so I have 1 hour to explain to you about that, but so let's wait with that question until the end, I think. And yes, but I want to say just that I'm going to use the terms doctors, interns, and residents, and most of the time I'm going to use the same. I'm going to mean the same thing, even though the proper term is interns. Yes. Yeah, so there are some special deals to make there are some special conditions to make the deal a bit sweeter, but you still don't want to go to a rural hospital usually. But yes. So as I said, there are 23 hospitals participating in the match. There are a few more hospitals in Israel, but they don't get interns. In 2013, there were about 450 interns that completed their studies in Israel, not abroad. Though, as I said, there are about 500 more that come from abroad, and we match them in a separate procedure. And the number of positions exactly equals the number of interns, okay? How should we assign interns to hospitals? So that's not what I wanted to. Okay, so first I should mention why do interns have any preferences over hospitals, right? So basically the internship is a short period of slavery within the hospital, but you might have preferences over where you want to be a slave, because you might have family in a certain part of the country, or maybe you just you lived all your life in Jerusalem, now you want to move to Tel Aviv. Or maybe, and I'm not, this is part of the issue here, that if you do your internship in Tel Aviv, you might form connections that will help you get a residency in Tel Aviv. And if you do a residency in Tel Aviv, you might later get a position in Tel Aviv. So you want to form connections in the right places. So most people in the country, most interns would prefer to do their internship in Tel Aviv or the area surrounding Tel Aviv. Some of them would very much like also to get to Jerusalem, because Hadassah hospitals around here are considered very good, and they give a lot of responsibility to interns relative to other hospitals. So what should we do? Should we let the doctors decide where they want to do their internship? The answer is definitely not, because if we let them decide, they would just all go to Ichilov in Tel Aviv, which is a very good hospital in the center of the country, and we won't get anyone doing their internship in Eilat or Beersheba, the southern cities of Israel, or up north. Should we do a two-sided matching? Should we ask doctors for their preferences? So this starts to answer your question. Should we ask doctors for their preferences and then ask hospitals for their preferences over doctors and do some kind of stable matching? So again, we don't want to do that, because then Ichilov, the good hospital in Tel Aviv, would just pick which doctors they like best, and they will get all the good doctors, and all the bad doctors would go somewhere else. Okay, so we don't want to have the good doctors going to Tel Aviv and all the other doctors going somewhere else. Should we just do a random permutation, just assign doctors, by random? And the answer is also no, because while we'll get uniform quality across hospitals, we won't get, we're completely ignoring doctors' preferences. And it might be that there is a very good doctor who actually wants to do the internship in Eilat. So we want to send them to Eilat, okay? And we don't want to send them to Tel Aviv. So here are the principles for assigning doctors. We want to have uniform quality, or almost uniform quality across hospitals. We want to determine capacities. We are determining the capacities. We are now in the role of the state. We're determining the capacities, and we want to according to size and according to geography. We want to compensate hospitals that are far away because usually they have some problem in recruiting expert doctors, people who already finished their long track. So we want to compensate them by giving them a bit more interns.
Just wanted
Yes.
to ask about the uniform quality.
Yes.
If you believe in efficiency, there might be some argument for positive absorptive action.
So we don't believe in efficiency in that sense. We believe that we don't believe in efficiency. We believe that even the distant cities should have good doctors. But yes, we might. It's interns. It's not experts. You know, you might want to put an expert where all the good equipment is, right? But an intern is just cheap labor.
But if they're still learning, you might want to have the
Yes,
the
it's true.
talented people
It's true.
learning.
It's true. So this is not a condition in this specific match.
How do you disentangle?
Okay, I'm moving on. Okay. So we also want to have fairness among doctors, and this is a slightly flexible concept. First of all, because we cannot just give all doctors their first choice. Somebody is going to go to, I don't know, Naharia, which is nobody's first choice. It's a small city up north. It's really nobody's first choice. I looked at the data. Good question for another talk. There is talks upstairs about I think the Middle Eastern stuff. So maybe you should ask them. But when I'm saying it's a flexible concept, we also sometimes want to take into account certain situations, such as doctors who happen to have children, and we want to give them more flexibility in choosing where they go. For example, if they're already based in Beersheba, we don't want to move them to Tel Aviv and have to move their children. So there are special conditions for parents. There are also special conditions for people who did really, really well on their final exams, in the medical studies, just because we want to encourage them to study well. But subject to the above, we want to make interns as happy as possible. So now, framework. This is called the assignment problem. And you shouldn't confuse it with another thing called the assignment problem. So both in market design, okay? So this is the assignment problem. We also have a paper by Shapley and Shubik from 71 or so, talking about matching firms and workers with transfers, a two-sided matching thing. It's called the assignment problem. When you search the literature, be sure that you are searching for the right thing, okay? So we have a set of objects, and we have a set of agents. Each agent has preferences over which object you would like to be assigned to. And objects do not have preferences over agents. And the question is, how do we allocate the objects to the agents? And again, this is not the other assignment problem. We have no monetary transfers. Okay, so I cannot pay somebody and get their assigned object, not before the fact, not after the fact. But in fact, we actually had, not me personally, but the medical system had problems with people getting matched and then paying other people to switch. So up until 3 years ago, people would, you'd find a lot of people that suddenly come and say, you know what, I never thought of it, but I really want to go to Nahariya and give this position in Tel Aviv to the other guy who went to Nahariya, and I want to make a switch with them. And if you ask them later, you see that they got paid a lot to do the switch. So 3 years ago, it was decided that switches are now, let's say, almost impossible to do, specifically for the most demanded schools. Where was I? Yes, so one motivation for the assignment problem is the medical internships that you talk about. Another is what Attila talked with you about yesterday about school choice. Another one is what Eric Budish talked with you about course allocation. There is apparently also a problem of assigning students to thesis advisors at the Hebrew University. So this is another opportunity to think about the assignment problem. The NBA draft is another example, even though players actually have, preferences over where they're assigned at the point in time in which they conduct the draft, it's the teams that choose the players, okay? And there are many more examples. So what do we care about when we do the assignment problem? Two leading requirements are always fairness and efficiency. You'll always, when you talk with practitioners, you'll hear that we want our system to be fair, to give equal opportunity to everyone, and we want it to be the best, you know, as good as possible. And this is not what we think about usually when we think about two-sided matching, right? In two-sided matching, we think about stability. Here, we cannot think about stability because the objects do not have preferences. There are other questions that, you know, people won't tell you, but you need to think about. First is strategy proofness. We want our mechanism to make it safe for students, for doctors, interns, whatever, to report their true preferences. If they need to cheat and manipulate and do stuff like that, it becomes a bit harder for them. And also, it becomes hard for us to study the results of this mechanism. A mechanism can be non-strategy proof, but very difficult to cheat, okay? So for example, I think probably you heard about the Boston mechanism in one of the talks here. And in the Boston mechanism, it's very easy to cheat because you know which schools are demanded and you know not to apply to those schools. But in other mechanisms, it could be a bit more difficult to cheat. Another thing that you really should think about is when people tell you that this is the case for an assignment problem, is it really? Could it be that the objects actually have preferences and you just decided to ignore them or to not treat them in the model, okay? If they do have preferences, you might find yourself in a bit of a problem because the system that you design will affect the behavior of objects. Even if they cannot report preferences, they might strategize in another way. For example, a hospital does care about which interns it gets, right? So the hospital can provide scholarships, for example, for excellent students that would be assigned to it. And then this will make excellent students raise the hospital in the ranking, but students that are not that good would not raise this hospital in the ranking, and maybe this would help the hospital to get better students. So it's very important to note whether the objects really have preferences, and if they do, think about how the design that you are suggesting would affect their behavior, okay? But we're going to ignore that from now on in this talk. So let me move to the first and easiest mechanism in some sense that you already heard about, random cell dictatorship. The definition is very easy. Agents are randomly sorted, and then each one in return picks the object she likes best among those that are still remaining.
What was used, right?
What's that?
That's what was used before it came, no?
Maybe and maybe not. Don't ruin my talk. Yes. So, advantages of this mechanism. First, it's super easy to understand. Why it is important that it's super easy to understand? Because you need to go to people and explain to them, this is the mechanism that you are going to use. Do you like it? And they should understand what they are saying, what they are talking about, right? Actually, also because it's super easy to understand and super easy to think about, people actually, this is the baseline. This is what people usually do when they have no other idea what to do. It's also easy to implement. You can give any programmer the assignment to write it, and he's not going to have any problem with writing it. It's fair because everybody gets the same chance of getting the first object and so on. It's strategy proof because, okay, so when I'm being called to select an object, I want my true preferences to be in the system, because if I have other preferences, the system might select an object that I don't like best among those that remain. So it's very easy to say that it's strategy proof. It's also ex post efficient. Why is that? Because ex post efficient means that nobody wants to trade after the fact, after we have a realization. Because the first student, the first doctor, got the object that she likes best, right? So she doesn't want to trade. The second doctor got the object that she likes best, maybe except for the object that the first student got, but the first student doesn't want to trade, so the second doctor is also happy, and so on. Okay, so it's ex post efficient. And we'll see later, because it's so simple, you can easily extend it to more generalized environments. The same description that I just said here would work for anything, basically, any kind of problem. Yes? So we'll talk about that in a few seconds. It's true. there are a lot of concerns in certain, in certain applications, there are a lot of concerns about corruption, and we'll see some ways to solve that. Yes, Yanai.
Who's the body of the match?
Good. So let me defer this question to a bit later. Another question? Okay, good. So, is it really easy to implement? I said that it's 2 lines of code, and given everybody's preferences, it's, anybody can do it, right? However, let's look at few applications that tried to do it and didn't have, such easy life doing that stuff. So, the French choix de poste d'interne, which is the medical match in France, but unlike the Israeli medical match, this is not about internship, this is about residency, specialization, okay? So you need, once you finish your studies, 6 years of study, you do the national exams, and then you have to pick a specialization. That means you need to pick a field and a location. You need to know in which hospital in France you're doing your residency. It's not a random serial dictatorship. It's just a serial dictatorship because everybody is sorted according to the score in the national exam, and the guy who got the highest score starts first, and then the second, and the third, and so on. And how do you do that? So up until 2011, everybody just came to Paris from all over France to a giant hall with a giant screen, and the giant screen would show you the positions that are still left, and everybody would just go in, say, oh, those are the positions that are still left, I'm picking that one, and that would go off, and then he would go back to Normandy or wherever he came from, and the next guy would come in and choose from the positions that are left. And they managed to do it, they managed to go through almost 700 interns going into this hall in Paris every day. It's still not all the interns, it took some time, okay? It took a few days, even with this strange, very quick process. Do you have a question, Scott?
How long did each intern get to make a decision?
What's that?
How long did each intern get to make a decision?
So you know beforehand what are all the positions that are available, okay? And you know your ranking. So you kind of know what positions you might get or might not get. So you might be a little informed about what's going to be the feasible set, thanks. But you're not sure, especially if you're one of those that are in the 500th place, okay? In 2011, they got computerized, okay? So now they have not a giant hall, they just have a website, and you go into this website, and this is a picture from the frequently asked questions on the website. Let me sort of translate, I don't actually know French. So it says, you still have time. Your score was number 3,644 in the national exam, and right now number 51 is choosing a position. So you can go to the toilet, you can do whatever you want, you still have time, okay? And when your time comes, it says, you're now in the giant hall. They call it the virtual giant hall. You're now in the giant hall, and it's your time to choose. Please be considerate of other people waiting for you to choose.
You have it says you have as much time as you want. That's what it says.
It says it's true. You have as much time as you want, but please be considerate of other people waiting in line. And you can pick your position, and you might think that giving people as much time as they want is not the best recourse because, for example, this guy here has already been able to choose for the last 2 days, 25 minutes, 51 seconds. Okay, so this guy really took his sweet time. They know that it might take a while. If everybody takes 2 days to pick a position, in 10 years we might have the entire medical match. So they actually send you an email saying, on this day, those 10 minutes, you should be online and you should pick a position among those that remaining. And hopefully, when those 10 minutes come, you're online, you're checking the computer, and if you are not, then they will call you. And if you don't answer the phone, they will call you again. And if you don't answer the phone for 5 times, they will pick a position for you according either to preferences that you set in advance, but might not be relevant now that people already chose, or they might pick something randomly for you. It still takes a lot of time. They managed to do now 500 people a day, okay? So slightly less than they were able to do before when they had the giant hall with the giant screen. Why won't they take preferences from student and run the serial dictatorship on the computer? There are too many positions, okay? You cannot pick your specialization and city in France. There are just too many of those, okay? You cannot possibly rank 500 positions. So that's why they don't do that. So it's fun to make fun of the French, but however,
You personally have to be careful.
yes, and yes, exactly. So Harvard is a big university. Yes.
So maybe they could think of ranking a few positions.
Yes, they could.
And then select like the options that specialization. And
Yes,
the rest
so-
rank, like,
so- Sure. So in terms of economic engineering, there is not a lot to do there. Once they decided on serial dictatorship, that's the mechanism, right? But in terms of actual engineering, yes, there is a lot to do. It could be done probably in a better way. But you know, moving from one giant hall to a virtual hall is already saving a lot of people a very long trip for being 5 minutes in the hall. So Harvard University is a giant university. It has a lot of money, so it owns half of the city it resides in, more or less. It owns half of Cambridge, and they have a lot of apartments, and they want to rent the apartments to graduate students that are coming in to study at Harvard. And they selected a similar method. They have a random serial dictatorship with a twist. The twist is that instead of, so it's kind of similar to what you suggested, instead of, you know, having a turn, and going into the system at the exact time where you need to go, you have you're assigned a time block, and within this time block you go into the system, and all people in the same time block compete for the apartments. It's first come, first served within the time block. So you need to, you know, 12:01 a.m. you have to be online and pick the apartment that you want. 12:02 the apartment is not there. You didn't press refresh on time, the apartment is not there. But it's still a bit better because you have an entire day to pick your apartment. Why do they do that? Again, there are too many apartments to rank, and we don't want it to take forever. Okay? So the same reason.
What's the size of the market in each time slot? How many?
So, do you know? I think it's huge because I've been on that lottery a few times, 3 times. Each time I got number 3. The third time block, and the highest I heard about was number 11, I think. So I think not a lot of time blocks, meaning a lot of people within each time block. And I never got the apartment that I wanted. Yes?
It's on the order of hundreds at least.
Yeah, should be.
And just measured by the number of apartments, it's very dead. And it's very, very, very low supply. It's trying to at that capacity index.
True. So when you graduate, you might not necessarily give the apartment back to the lottery. You might give it to a friend. You can do something like that by supposedly claiming that he's your roommate, and then you cannot vacate the roommate, so he keeps the apartment. Okay, the Israeli medical match. So as I said, there are only 23 possible hospitals and no specialization, so it should be possible to rank 23 hospitals, right? In fact, I recently had a discussion with the psychologist from the Israeli psychology match, where they claim that it's going to be very, very hard for the students to rank 5 programs. But the hospitals don't care about, the doctors don't care about that. They are intelligent. They can rank 23 positions at the same time. Psychologists are also very intelligent, but they are lazy. So up until 2011, everybody gets in the same room, same as in Paris. And to make things as random as possible, what's the most random thing you can do? So you want to avoid corruption. What's the most random thing you can do? You draw names out of a hat. Hat is the most random thing you could do. And yes, it's a big hat. And yes, they are not the first people to use a hat to sort people into position. And no, I'm not going to talk about magical sorting hats as a way to solve the assignment problem. Okay? But starting from 2011, again, computerized random serial dictatorship. Okay, very good. They submit their preferences and they run random serial dictatorship. As for corruption, they have a few people gathering in the same room. Each one picks a number between 0 and 2 to the power of 32, about 4 billion. And then they add those numbers modulo 2 to the power of 32, and that's the seed that they use for the random number generator. So supposedly, you can't be too corrupt in this procedure. If you know some cryptography, you can actually be very corrupt in this procedure, but never mind. Back to theory. Okay, so what's the problem with random serial dictatorship? The problem is that it is ex post efficient, but it is not ex ante efficient. Okay, so look at this example. We have 4 agents, 4 objects. The first 2 agents like object 1 better than 2, better than 3, better than 4. And agents 3 and 4 agree with agents 1 and 2 about the ranking between objects 2 and 1 and 4 and 3, but they don't agree about the order for those pairs of objects. They don't agree that object 2 is worse than object 1. They actually like object 2. Okay? If you run random serial dictatorship, this is the allocation that you'd get. This means that agent 1 gets a probability of 5 over 12 to get object 1, 1 over 12 to get object 2, and so on. How do we get to that? So let's look, for example, at this cell right here. When does agent 1 gets object 2? Agent 1 gets object 2 if agent 2 was first, picked object 1, and then agent 1 came along and picked the object that she liked best, which is object 2. Okay, so that's 1 over 12. Now note that this matrix here is not as good as this matrix right here. Okay, what happened when we moved from here to here? So agent 1 gave away 1 over 12 shares of probability of getting object 2 and got instead 1 over 12 to get object 1. And similar for object 4 and 3. And each of the agents here is happier than they were before, okay, under this allocation compared to this allocation. So in layman terms, random serial dictatorship gives an allocation such that nobody would like to trade when you already have the allocation, but people would want to trade before the lottery is made, okay, is conducted. Generally, we say that the mechanism is ex post efficient. So fine, I think most of you know that, but ex post efficient if nobody wants to trade after the fact, ex ante efficient if nobody wants to trade before, and ordinally efficient, this is something a bit new here, it means that we don't have people's utilities. We only have their ordinal preferences, and we don't want them to be able to trade based on the ordinal preferences. So it means that the assignment that we get out of the mechanism is not stochastically dominated by some other random assignment. Okay? And there is also a term called rank efficiency. I'm going to talk about this a bit later. That means that the distribution of ranks, so how many people get their first choice, how many people get their second choice, and so on, the distribution of ranks is not stochastically dominated by another distribution. Okay? If you're rank efficient, then you're ordinally efficient. If you're ordinally efficient, then you're ex post efficient. Okay? Yes? Ordinally? So if you're ex ante efficient, you're also ordinally efficient, but you can be ordinally efficient without being ex ante efficient. Because it could be that for some preferences, you cannot find a better stochastic allocation, but if you would have known the utilities, you could have found a better stochastic allocation. Okay? Maybe we'll see an example later that might make it more clear. Okay, so because random serial dictatorship is not efficient, we have a mechanism called probabilistic serial, which was suggested by Bogomolnia and Moulin. Thanks. Which is basically a simultaneous eating algorithm with uniform eating speeds. That sounds very easy. Let me explain. Even though you all understand, let me explain. So each object is a pizza, and we have portions of the pizza representing probability to be assigned to that object. So we have 4 objects, 1 to 4. Each one is a slightly different pizza. Each agent wants to eat pizzas, and they all eat pizzas at the same rate, 1 bite at a time. and they always eat from the pizza that they like best. So right now, agent 1 and agent 2 liked object 1 best, so they are looking at this pizza with this hungry look, and agent 3 and agent 4 look at pizza 2, and then they start eating it at the same pace. This is the uniform eating rate. And when they are done with the pizza, they are done at the same time because two people eating from each pizza, they are moving to the next pizzas that they like. Agents 1 and 2 like pizza 3, agents 3 and 4 like pizza 4, and they start eating the other pizza until they are done. And when all pizza were consumed, the content of each agent's stomach represent the probabilities with which is assigned each item. So for example, agent 1 ate half of pizza 1, half of pizza 3, so we get the probability half to get object 1, probability half to get object 3. And we got exactly the matrix that I presented to you before, okay? Now we need to conduct a lottery between deterministic assignments somehow. So for this matrix, it's very easy. Look at those two deterministic assignments. In this assignment, agent 1 gets object 1, agent 2 gets object 3, and so on. If we toss a coin and decide between this matrix here and this matrix here, we get exactly those probabilities for each of the agents. Okay? Now note that we cannot actually toss a coin for each agent separately. If we've tossed a coin for agent 1, now agent 2 we already know where it goes. Okay? So we cannot possibly do it by independent coin tosses. And this is even clearer when we look at a different matrix that we could have got out of the probabilistic serial. If we had this matrix, how do we know that we can actually find a lottery over deterministic assignments that would give us those probabilities for each of the agents? And the answer is we can. Okay? There is a theorem called Birkhoff-von Neumann theorem. I'm going to mention it later in more detail. That basically says it's fine, don't worry. You can do that. Okay? You can find the lottery between deterministic assignments. Some properties of the mechanism. Okay? So it's not very easy to understand, or more important for us, it's not very easy to explain to people how probabilistic serial goes, even though we know this nice animation I think can explain to most people. It's not very easy to implement. It's still not very difficult to implement, but it requires some programming effort. It's fair in the sense that in any point in time, every agent could have eaten what any other agent could have eaten, right? It's also envy-free. We're not going to talk about that. And it's ordinally efficient. Let me try to give you a sense of a proof why it is ordinally efficient. So suppose that it was not ordinarily efficient, and there were two agents, agent I and agent I prime, that would like to trade what they got, the probabilities that they got. Agent I got probabilities, some probability of getting O, and agent I prime got some probability of getting O prime. And now they want to switch. It means that I likes O prime better than she likes O, and I prime likes O better than she likes O prime. Okay? Suppose, without loss of generality, that I ate O before I prime ate O prime. Okay? So when I ate O, I prime was either eating O as well, or was eating something else that was better for I prime. This means that he only ate pizza O prime after pizza O was consumed, right? Because as long as pizza O exists, he wants to get stuff, he wants to eat of pizza O. But then it means that when pizza O was consumed, pizza O prime still existed, right? So why did agent I eat from pizza O when he could have eaten from pizza O prime, which he likes more? So this is a contradiction, okay? This shows you that there cannot be two-sided trades between agents. And similarly, you could show that there couldn't be any more involved trades, and you get ordinal efficiency. Probabilistic serial is not strategy proof, unlike the random serial dictatorship. Let's see an example. Agent 1 likes 1 better than 2 better than 3. Agent 2 likes 1 then 3 then 2. And agent 3 likes 2 then 1 then 3. What's the probabilistic serial assignment? So we're going to do it, just to get even more acquainted with the probabilistic serial. So first, agent 1 and 2 eat pizza 1. Agent 3 eat pizza 2. And after pizza 1 is consumed, agent 1 got half of it, agent 2 got half of it, and agent 3 has eaten half of pizza O2. Okay? Then agent 1 starts helping agent 3 with eating pizza O2, and agent 2 goes and eats pizza O3. Okay? When they are done, they are all eating pizza O3, and this is the distribution that we get. Okay? Now, what would have happened if I3 reported that he liked pizza 1, object 1 better than object 2 better than object 3? In this case, they all would have started by eating object 1, right? Each would have got a third. That's fine?
Yeah, it's like I won now.
It's like I1, yes.
Yeah.
So everybody
it goes
would have,
together with I won also.
yes. So everybody would have eaten object 1, then I1 and I3 would have eaten object 2, and then everybody would finish pizza 3, okay? Now, note that this matrix here does not dominate this matrix here, but look at what agent 3 got. Before, he got 3/4 probability of getting his top choice, and 1/4 to getting his least preferred choice. Now he's getting only half probability of getting his top choice, a third to get the medium choice, the middle choice, and 1/6 to get his least preferred choice. Think, for example, that object 2 is doing a PhD at Harvard. Object 1 is doing a PhD at MIT. So both of those options are very good, very close by. They're not very different. Obviously, we have some preference for Harvard over MIT, but not a big preference. And object 3 is doing a PhD at the West Eastern Catholic University of South Dakota. So it might be very important for me to move from 1/4 probability of doing a PhD at the West Eastern Catholic University of South Dakota to getting only 1/6, and getting a bit more probability of studying either at Harvard or at MIT. It's not a real university. So it's not strategy proof. Let me just tell you that it is what is called weakly strategy proof, in the sense that nobody can manipulate and get something that's stochastic that dominates the allocation that she got before. Okay? But I'm not going to prove that. What happens when we look at larger markets? Okay, so I think somebody mentioned probably Itai mentioned some results about large markets. There are also results about the assignment problem in large markets. So Fujito Kojima and Mihai Manea showed that probabilistic serial is approximately strategy proof in large enough markets. So if you look at the big market that has some random element to it, there are some technical conditions that we're not going to go into. You can say your true preferences and you're not going to be very wrong. Okay? It's almost the best reply. The downside is, as was proved later by Che and Kojima, is that when you look at large markets, probabilistic serial and random serial dictatorship are almost the same. Okay, so the probability shares that each agent gets, they converge in the random serial dictatorship and in the probabilistic serial. And in fact, Liu and Picha showed later that this result is actually more general than just talking about probabilistic serial and random serial dictatorship. Any mechanism which is asymptotically efficient and symmetric, meaning that it treats all agents the same, and asymptotically strategy proof, converges to random serial dictatorship. Okay? So you can never get a matrix which is very different from the matrix we got before. Yes? I can't hear. Second? Oh, the usual one. I don't remember the. No, you're right. It could be that one agent would get something very different, but not too many agents. It's something like that. Okay, I don't remember the specific technical conditions, but I can refer to the paper later. So let's look at our market, the Israeli medical match. Okay, this is data from 2011. We have in 2011 there were 378 interns and only 20 hospitals that got positions for interns. This is the distribution. This is the rank distribution of random serial dictatorship. Okay, you see that about 40% of the people got their first choice, and about slightly more than 80% of the people got either their fifth choice or better. Actually, this is C index. It's sixth choice or better. And now I'm going to show you the result from running probabilistic serial on the same market. There it is. Okay, do you see any difference? There is not a real difference between those two, even in a market as small as. What's that?
The location could be different.
This is only the rank distribution. This is only the rank distribution. But this is for 380 doctors, and we get the difference in rank distribution is fraction of a percent. Okay, it's very, very small. Second?
No, that's 2011.
Yes, but in 2011, for some reason, there were only 20 hospitals. I'm not sure why. Maybe they split or something. So, let me tell you about another mechanism to solve the assignment problem before I move to our solution.
When you, sorry.
Yeah.
So you run here the random algorithm and look at the distributions that you get from running each one of the two.
Yes.
That's what we see here.
Yes.
So when you say zero, so that getting the first choice is 0.4, that's the average over
All people
the
in
rounds.
yes.
I would suspect that the rank value mechanism would be different. Did you run that as well?
What's the rank value
The rank
mechanism?
value mechanism, the rank efficiency, rank value.
Sure. So we're going to talk about that in a second. Okay. You mean?
And I mean this one. That does mean.
Yes. Good. So we're going to talk about it in a few months. So just another mechanism before we move to our mechanism. This one is much older than the others. It's from '79, based on work by Hillen and Zeckhauser. Actually based on Harvard housing, but not the graduate housing, the undergrad housing. So the algorithm is each agent submit their utility function over vectors of probabilities, and each agent is endowed with equal probabilities. And for getting any object, we find a price vector that clears the market, okay, the market for probability shares, and we get the equilibrium allocation, and then we have this matrix, and we decompose it into a lottery over deterministic assignments using the Birkhoff-von Neumann theorem, okay? I said here not very easy to understand. It's actually very easy to understand if you're an economist. If you try to explain it to other people, you might get into a bit of trouble. Why is there a price that clears the market and so on? It's not very easy to implement. It's fair though, because given the prices, everybody can buy the same thing. And it's Pareto efficient because of the first welfare theorem, right? It's a market, so everybody gets the entire distribution is, the entire allocation is Pareto efficient. If it's Pareto efficient, it's also ordinally efficient. It's also ex post efficient, right? What's the problem? It requires people to submit utility functions. And now, this guy here has a car utility function that he really thinks is great. And this girl here has a different utility function. It's actually pretty hard to ask people for the utility function. Actually, they might not be aware of what their utility function is, and definitely they're not able to write it down. Okay. And also, like the probabilistic serial mechanism, it is not strategy proof. Okay, because you can report different preferences that would somehow affect the prices, and then you somehow benefit from changing the prices. And again, it's strategy proof in the large. If the market is large enough, then by submitting false preferences, you cannot affect the prices, or not by a lot. So you want to, it's almost strategy proof. You can report your true preferences and nothing bad would happen. But again, suppose you don't ask people for their cardinal preferences, you ask them for their ordinal preferences and you just plug them into some kind of utility structure that you already have in mind. So you again have the result by Lewin Pitches that says if you are submitting ordinal preferences and you are approximately strategy proof and you are approximately efficient and you are symmetric, then you're going to get a distribution which is very similar to the random serial dictatorship. Okay? So now we finally arrived to the Israeli medical match, and this is based on joint work with Slava Bronfman, who is a student at Bar-Ilan University, and Avinatan Hasidim, a professor at Bar-Ilan University, and Natan Efek, which happens to be the CEO of the Ministry of Health. And this is very good to have somebody from the Ministry of Health right next to you when you do stuff like that, especially if it's the CEO. We had a few so how did we get to redesign this match, actually? The people so this comes back, I think, to a nice question, right? The people in charge of the match are the Ministry of Health, but they give the authority each year to a committee of 6-year students that are being elected in each medical school. And those students decide on how to perform the match this year. So in 2011, Avinatan went and talked with them and said, you know what, I think we can do better than what you do. And they said, we're not interested. So in 2012, he came again. And now it was a different committee because every year they changed the committee. And they said, who are you? And he said, I'm Avinatan. I was here last year. I want to suggest something. And they said, no, we're not interested. And then he came again. And at some point, after the third year or fourth year, they said, you know what? Okay, fine. We can try that out. We'll do a voting across all medical students. If you'll get a majority, we'll do that. And they did the voting, and they decided that they want to go with a redesign, okay, with our suggested algorithm, which they didn't know much about, but they knew it was more efficient, okay? So what's the requirement? First requirement, do not make anybody worse off compared to what they were under the old system. If before they got some probability of getting to their first choice and second choice and so on, make sure that they feel better about the new algorithm compared to the old algorithm. Second, if you can, make it more efficient, okay? And how does that work with what I just told you? So there is an efficiency strategy proofness trade-off. We have to play a little with strategy proofness, okay? We have to somehow make it not strategy proof so we can make it more efficient. And this goes to your question about rank efficiency. So we can actually improve rank efficiency but not using a strategy proof mechanism, okay? And this is a great work by Clayton Featherstone from 2014, actually a bit earlier, but he has a new version. And in fact, we're not even the first to do it because Clayton and Al here already redesigned 2 mechanisms that try to maximize the rank efficiency of the rank efficiency of the distribution. One is for Teach for America, an organization that assigns recent graduates of top universities in the US to teach in American schools. And another is the HBS Field 2, which is kind of a program for sending MBAs to different countries, supposedly to learn. Yes?
So your requirement to do no harm is given fixed preferences do no worse than RST, right?
Right.
Or is it given the fact that it's not strategy proof and people might be now misrepresenting, so you still won't be harmed by their misrepresentation?
In some sense, you are right. But in another sense, you're completely wrong in the sense that nobody knows what strategy proofness is among those doctors that we talked with, right? So they don't care about what you just said. They don't know that people are going to cheat. So no, they care about comparison to the reported preferences, okay? So here is our mechanism. Compute the random serial dictatorship probability shares, because that's our baseline. We want to make everybody at least as happy as getting their random serial dictatorship shares. Solve a linear program to maximize social welfare. I'm going to define in a second what social welfare is, with constraints that nobody get less utility compared with their random serial dictatorship probability vector, and that hospital capacities are respected. And finally, we run the lottery using the Birkhoff-von Neumann decomposition again, okay? So it's very similar to the Hill and Zeckhauser process, only we solve it with a linear program. Utility, to know what utility is, we just ran surveys, a lot of surveys among students to see how they treat different probability vectors, and we came up with an approximated structure of utility that given some ordinal preferences, we can plug them in and assume that those are student utilities. Obviously, it's only an approximation. It's not actually their utility, but that was good enough in order for us to use this mechanism. Social welfare here means just the sum of utilities of everybody. Yes?
In Hill and Zeckhauser, you start from equal probability.
Sure.
Here you're starting from the RSD probability. So is this a competitive equilibrium starting from the RSD probability shares?
So not exactly, because we plugged in a few other things into the maximization. We cared about, so It's more or less that, but not exactly, because of some other stuff that we added in. For example, treatment for parents, for example, treatment for couples that I'm going to talk about, and something that I don't want to get into here, but I can tell you about later. Okay? Yes?
Do you have to do the surveys every year because some hospitals might evolve into better options?
Sure, but the surveys were only to determine the general structure of utility, not the ranking of hospitals or anything like that. So I could have put here like the utility form that we choose, but it's not very enlightening. It's just some formula you plug in. What's your first choice? What's your second choice, and so on? What probabilities you get, and you get the utility. Yeah.
Is that the utility where you say, okay, any first choice has a certain utility, and then any second
Yes,
choice?
exactly. Something like that.
You're basically eliciting the rank value, like the social rank validation.
Yes. Yes.
Okay. So that doesn't really fit with your constraint that nobody should get less utility.
Well, it fits as if you believe that those utilities actually represent people's utilities.
Right.
It's,
Okay, so you have to do that.
yes. So I'm jumping ahead, but let me just tell you that we actually ran the match, and what we are doing now is we're running surveys ex post to see that we just ask people whether they like better the random still dictatorship assignment or what they got using our mechanism, and we actually tell them, look at those two probability vectors and decide among them. They don't know what really happened in the mechanism. They only know what assignment they got eventually, right? So we hope that they would rank what they got from our mechanism above what they would have got from random still dictatorship. If they wouldn't, it would be a big problem for us. Yes.
For the ex-ante which are the probability vectors, what they got, what they actually got.
Probability vectors are ex ante.
Yeah, but do they
If I show them what they actually got, they're either happy or not happy, depending on their preferences. If somebody went to an area, he's not happy.
they also know that they got very low preference. They got exposed, they got something bad. You're asking them to be happy about the
I'm not telling them this is what you have got. I'm just telling them please answer the survey about those probabilities. Yes, it's not about what they actually got, because eventually they just got allocated to some hospital. Yes, Scott.
So that-
Oh, sorry. In random still dictatorship, you get positive probability for almost everything. So they cannot say that, and in our allocation, you get positive probability for what you were assigned. So they cannot tell by where they got assigned which probability vector they had before.
So they have to compare vectors of length 23 of probabilities, or
Amazing,
they just
but
change two coordinates?
no,
and
they
then-
had to compare vectors of length 23, and I was opposed to that, but apparently that's what they wanted.
Not vectors that differ in just say two coordinates.
No, they are very, very
Very
different.
different?
They are very different. Yes, I also was skeptic, and I'm still skeptic about whether this actually is something that people can do. Yeah, Simon.
What is the, I mean, in the original RFC algorithm, how do you treat parents? How do they treat parents?
Parents.
And
So-
stuff like that. I mean, here you're moving from ordinal to cardinal using those virtual utility things.
Yeah.
You can twist it. How do they do that?
So in random cell dictatorship, you don't need to consider anyone's cardinal utility. Ordinal utility is enough. Okay. And as for parents, they had some. They had a backdoor. If a parent did not get what they should have got, then they moved them up the queue or something like that. It wasn't.
These are students who were already assigned, right?
What's that?
These are students
Yes,
who
yes,
were already
yes.
assigned. That's a problem.
It is. But we also
It's a
so
real problem.
the surveys that we did before were on students that were not assigned, right? The surveys that we do now are for people that are already
You
assigned.
have an excuse if you fail.
Definitely, we have many excuses if we fail. That's market design 101. Okay, good. So let me tell you about properties of the mechanism. Some of them we already discussed. So it's not easy to explain it to people. It's a linear programming kind of thing. Actually, we're just in the process of writing a journal article for one of the Israeli medical journals that only, most of the paper is explaining what linear programming is. It's not very easy to implement. It's fair. Everybody gets the same probability, the same treatment. It's symmetric. It's not strategy proof. For example, suppose that I want to go to Nahariya in my 5th place. Okay, and Nahariya is for most people it's around their 10th place. Okay, so I want it in my 5th place. I'm probably going to get a lot of probability to get to Nahariya. The linear programming program is going to give me a lot of probability to get to Nahariya, but it's also going to give me a lot of probability to get to Nahariya if I would have put it in my 6th place, right? And in my 5th place, I would have put something which is more popular. For example, some hospital in the center of the country. And then if I would have put the more popular hospital in my 5th place, I would have got some probability share from the random serial dictatorship at the beginning to get that hospital. And then the linear program would assign more, might assign more probability for me to get my 6th place. Okay, so I just described a manipulation. You might have followed, you might have not followed. The fact that it was not as simple as just don't apply to over-demanded schools means that it might be a bit harder to cheat in this system compared to other mechanisms. But it's possible, especially if, for example, you were born in Nahariya, you might, after some time, understand how it's possible to cheat this mechanism. Also, it's not strategy proof in large markets, because the same argument, the exact same arguments work even in a large market. So why do you think it's fine? Why do we think that it's fine to be non-strategy proof in this case? One reason is that if somebody finds out it is not strategy proof, we're going to know about it. It's going to be on Facebook. It's going to be specifically on their forum on the internet that we keep reading and see that nobody actually knows how to cheat this mechanism. Another reason, as I said, it's not very easy to cheat. It's even more difficult to cheat if you don't know what the mechanism is. And we didn't actually tell anyone what the mechanism is. So this is a very classic way of preventing cheating. You don't tell them the mechanism. It doesn't mean that they would never be able to understand how to cheat. It just means it will take more time. And when they will understand it, we might address this problem by changing the mechanism or doing something else. Okay? On the other hand, the fact that we are not strategy proof meant that we can actually improve the rank efficiency. So here you see the random serial dictatorship. This was done by, not by me, so the graph is a bit strange. It starts from 200 right here, okay, and that's the number of interns. So again, it's about 40% to get your first choice, and about 80% should be 80% to get your 6th choice or below or above.
The blue is the random?
The blue is the random serial dictatorship. Okay, thanks. The green is our mechanism, and you see that we actually, for the first place, we did not improve by much. Maybe 20 more people get their first choice, but about 100 more people get their 5th choice or better. So it's a big difference, okay? And they really liked, this is how we solved the mechanism, by showing them something that looks like this. Yes? No, this is rank order efficient. This is how many people got their first choice, second choice, and so on. So this has nothing to do with the utilities that we generated. What you might say is that this is according to preferences that were submitted that might have been manipulated. But obviously you could run the same process. This is on 2014 data. You can do it on data from before, when preferences were submitted truthfully, hopefully. And see that you get the same efficiency gap. Yes?
The fact that the green line goes into the line
yes.
either means that you are doing some harm, right?
Supposedly, yes. Yes, I think it's small enough that nobody would care about that, but you're right. We are helping a lot of people getting their 6th choice, but maybe we're harming some people that instead of getting their 15th choice, got their 16th choice, but not a lot of them. Yes.
That's only ex post, right? Ex ante you are by algorithm.
Yes. Yes. Yes.
No, don't we get set with all those stochastic numbers?
Say again?
Don't we get set with all those stochastic numbers?
Good question. I'm not sure. I need to check that. Probably we do. So, yes.
The fact that this is not strategy proof in the case of large markets should mean, I had asked the question earlier about whether this was Healy-Zeckhauser, but with different initial endowments.
So,
that, if it were Healy-Zeckhauser, it would be strategy proof.
So, it is similar to Healy-Zeckhauser with different endowments, but the endowments themselves, the different endowments are
Oh, I see. So
determined by your preferences.
I see. So that's what manipulation does. So.
Yes, you manipulate the initial endowments that you get. Yes.
Yeah, I just wanted to react to your question. You are using, to come up with this assignment, you are using the utility structure that you came up with, right? You use it in the mechanism.
Yes.
But you're not using it as reports from the agents. You're using it as some maximization.
Yes. Oh, okay, thanks. Good. Okay, so it's common in those summer school to suggest some open questions to students, so I thought this might be a good place to do that. So we saw that there is an efficiency strategy proofness trade-off, but I think there are two questions that should be asked here. One of them is, are there situations, can we think of some cases in which this trade-off is not that important or less important? Okay, for example, you can think that instead of being able to report all possible preferences, you are not allowed to report Nahariya as your first place. Just because nobody ever reported Nahariya in the first place, then you are not going to be able to do that next year. And that might reduce the possibilities for manipulation. So are there some structure of preferences that would allow you to be more efficient? This is one question that I think is interesting. Another one is, can we design, so I suggested a mechanism and claimed informally that it is not as easy to manipulate as some other algorithms. Can we find a way to either quantify that or actually find a mechanism in some environment in which it is computationally hard to find a manipulation? Okay? Because if we can, then we might get closer to rank efficiency without really hurting strategy proofness in a way that upsets us. Okay? Because the default value, I think, for everybody is to say their true preferences. Okay? So you need to start from true preferences and somehow search for a good manipulation. Let me tell you about the Birkhoff-von Neumann decomposition, because as I said, it was important. I used it 3 times already in the lecture, and I didn't say anything about how you do that. So what we had in each of the cases are matrices that the rows sum to 1, meaning that every doctor gets assigned somewhere, and the columns sum to the hospital's capacities, right? And this kind of reminds us, some of us, of bistochastic matrices such in which every row and every column sum to 1. Okay, so we're going to state the theorem about bistochastic matrices. And the theorem is that any bistochastic matrix can be represented as a convex combination of permutation matrices. Permutation matrices, those are the valid deterministic assignments. Okay, those are the 1s and 0s. So here's the proof. It's going to be slightly mathematic, but really you can handle that. Suppose A is a n by n bistochastic matrix that has k elements equal to 0. So it has n squared minus k elements that are positive. All the others are 0. What we're going to do, we're going to move to a new matrix. We're going to remove some part of the convex combination that we're looking for and move to a new matrix that has k plus 1 elements. And then we're going to do it one by one until we get to all the elements being 0. So think about a bipartite graph, two-sided graph, with an edge ij if the element in the matrix is positive. Okay, if it's 0, we don't have an edge. Now note that for every set of rows, every set of doctors, we have that the size of the set equals going over all the doctors in the set and summing all the elements in the row. Okay, that because the sum of each row is 1. this is equal to going all the doctors in the set, but now summing only on the hospitals that have positive element in one of those rows, okay? Which is smaller than going over all those hospitals, the hospitals that some guy from U has a positive probability to get, and summing over the columns, okay? Which is exactly the size of the neighborhood of U, okay? So we got for every set U, the size of U less or equal the size of the neighbors of U, which is exactly the condition that we need in order to find a perfect matching in a two-sided graph. This is Hall's theorem, for those of you who know it. For those who don't, this is incomplete proof, okay? So we found a matching in the graph, a perfect matching, which represents a permutation matrix. Now we remove from A as most as we can from that permutation matrix without turning any of the elements negative, okay? So we do it just until at least one element becomes 0. And we got a new matrix that we can normalize to become B-stochastic again and do the same process, but this new matrix has one more 0 compared to the previous matrix, okay? And that's the what? That's the process. How long does it take? So at most we do n squared steps. In each step we need to find a perfect matching, which we can do using well-known algorithms in computer science that take about n squared time. So at most it's n to the power 4 time, which is not a lot, okay? I see that some of you are not impressed or don't care. Okay. Extensions of this theorem. So we can easily extend it to our case, in which hospitals have capacity bigger than one, just by splitting the hospitals to many positions, and each position would be a column instead of each hospital being a column. It also works for more doctors than positions, or more positions than doctors. We just add dummy doctors or dummy positions, okay? And Eric Budish, together with some co-authors, one of them is Paul Mirum that I think already left, proved that you can actually do it for multi-unit assignments, okay? So for each doctor to require several hospitals, and each hospital employing several doctors, or more likely think about course allocation. Each student wants to study several courses. Each course can have a few students. And you can also use it for real-world constraints, such as you want to accept at most 50% women, 50% men, or something like that. Okay, you can do it for other constraints as well. And you can even do it for a larger domain of substitutable preferences. Okay, you can have doctors having students having substitutable preferences over courses. Meaning, if I take real analysis 1, maybe I don't want to take algebra 2. Okay, stuff like that. In our application, there are couples in the match. Okay, so same as in the US, people get married either before or throughout medical school. You'd actually expect more couples in Israel because we tend to begin medical school a bit later. But there are not that many. We have about, in a market with about 500 interns, we have about 15 couples this year. Okay, so 30 people out of 500 are part of a couple. Maybe it's because it's not a very wise life decision to become a medical couple. Okay, it takes a long time to become a doctor. It takes a lot of your time every day. You cannot actually raise kids and so on. So you don't want to be a couple of doctors. And indeed, even some of those 15 couples are actually not romantically related. They are just people who said, you know what? I don't really care where I'm going next year, but if I'll be a roommate with that great guy, I would be happy. So let's sign in as a couple, sign up as a couple. But if you're a real couple, not some two roommates that want to be together, you have your preferences are actually represent some form of complementarity, because you don't want one of the people to be in Nahariya and the other one to be in Eilat. Nahariya is very is up north, Eilat is down south. It's about 4-5 hours drive probably. You don't want this commute every day. What? 7. Okay, even bigger than I thought. So it's a complementarity, and as in the two-sided matching, it's going to be a problem for us. Sorry. Now, in order to accommodate for couples in previous years, what they did is they just told them, okay, you can rank all the hospitals. You get only to rank together one list. You cannot rank pairs. You rank, I want to be, either both of us goes to Ichilov or both of us goes to Soroka, and so on. And in the random cell dictatorship, you get one note in the hat. And when your name is drawn, you pick the hospital that you like best that still has 2 positions open. And if you're one of the last people to be called and there are no 2 positions open in any hospital, then the couple is split. Okay, that's what they used to do. And we want to do a similar thing in our solution. So how do we do it? And now it's joined with Noga Alon, who joined us, just to prove the difficult theorem. So, assume that couples cannot be split. This is an example, okay? It's not theorem yet. Assume that couples cannot be split, and both hospitals have 2 positions, and there are 2 doctors in the market, D1 and D2, and the couple C1. Suppose we now ran our algorithm, and we got to this matrix right here that supposedly promises Dr. 1 3/4 probability to get to hospital 1, and Dr. 2 1/4 to get to hospital 1, and the couple half to get to hospital 1 and half to get to hospital 2. Okay? This is legal because this one always get assigned, this one always get assigned, this one always get assigned, and the sum here is actually 2 because this half here should be multiplied by 2. There is a couple there. Okay? We cannot possibly decompose this matrix into a lottery over valid assignments because wherever C1 is assigned, they are getting all the hospital, right? And then D1 and D2 should go together to the other hospital. So D1 and D2 must have the same probability for being in hospital 1 or hospital 2, or we're using inefficient assignments, okay? More generally, deciding whether a given matrix with couples that meets all the right requirements can be decomposed into a convex combination of valid deterministic assignment is NP-complete. Give me a matrix and ask me, can you decompose it to a lottery? The answer is, I don't know, I'll get back to you, but you won't. And note that the fact that we only have couples, we don't have triplets or anything bigger than that, and the fact that couples are restricted to only give us preferences over hospitals and not pairs of hospitals, this doesn't help us here, okay? Because in fact the problems are just as hard when they are restricted and when they are not restricted in the preferences they can submit. Luckily, we can approximate, okay? So we cannot actually solve, but we can approximate the solution. So suppose that there are more singles than couples, and that all doctors must be assigned and all couples must be assigned together. And I didn't write it here, but this means that we're always using valid efficient assignments, okay, deterministic assignments. We can find a decomposition that approximates a given matrix up to something that looks like 1 over C, where C is the smallest capacity of any hospital. Okay, look at all the capacities, look at the smallest capacity. We can approximate to that extent, which means that I'm going to give you a lottery over deterministic assignments that if you compute the probabilities that each agent they get something very similar to the probabilities that they were assigned up to 1 over C. Okay? I think I'm not going to prove it now. But there are examples showing that this is tight. Okay? You cannot do any better than that. And if there are more couples than singles, you can't do anything basically. Okay? What's next? So it went well. We did it already. It went well. Everybody was happy. We're now running the surveys that I mentioned before to see whether people utilities were correctly approximated by just comparing not some random vectors that of probabilities, but the vectors that they actually would have got under random dictatorship and what they got under our mechanism. And in fact, the Ministry of Health people were so happy that they decided that they are going to use it next year for those interns and also for the interns coming from abroad, which also have a match. So, in fact, right now, Avinatan and Slava, two of my co-authors on this project, sit with the Ministry of Health people in Tel Aviv and give them the code and explain to them how to run the system for next year for the non-Israeli schools.